Pleasure to be back in Princeton. Most of my co-authors are in the audience, so they can correct me as they go along. This work was done mainly with Nick Stone, but with old work with Scott Tremaine. And I'm going to address a topic which is so fundamental, it's hardly ever addressed, and that is, where do the black holes come from that we find in the centers of galaxies? There are many fantastic papers, and I've written some of them, where you imagine extremely high density situations from cosmological simulations, and you have direct collapse of matter, which makes a black hole. But you might as well just draw a picture of a black hole and say you made it that way. I find even my own papers on this quite unconvincing. And so looking at the evidence for where you find them and what are the simple dynamical processes that could produce them as an explanation. And the particular one being examined is tidal capture runaway. So the background is nuclear star clusters. We see them everywhere. They're found in most normal, moderate mass galaxies. So they're not unusual. We're depending on something unlike direct collapse, which is directly observed everywhere in normal galaxies. They have very high densities, which include old, low-mass stars, small core radii, and masses ranging from 10 to the 5th to 10 to the 8th solar masses. That's observed fact. They have velocity dispersion, which several people have pointed out, for whatever reasons, is proportional to the velocity dispersion of stars in the galaxy. It's not the same, but it's proportional to it. So they seem to know something about the galaxies in which they live. They often contain early type O and B stars. There's something like 100 O stars in the central parsec of our Milky Way. There's a paper by Jeremy Goodman, who I think is in the audience, explaining how this will happen, that you, if you have a disk and it's unstable to fragmentation, that you can easily make a very top-heavy mass function. And we see it in lots of nearby galaxies. I don't think it's very anomalous, because otherwise we wouldn't see it in so many galaxies. So it may not be all the time, but if you take 100 O stars, their lifetime is 3 million years, it gives you a rate of formation. And at that rate of formation, you have a lot of black holes in the center. Now, every galaxy doesn't have 100 O stars in it, so you have to multiply by some duty cycle of roughly 10%. But you still get a lot of 10 solar mass black holes at the center. What's the origin of the nuclear star clusters? So we're still on that. Possibly in spiraling globular clusters with later addition of star formation. So there's two parts of it. Mainly old stars, which could be infalling globular clusters. And all of the details work out on what that is. There's an old paper with Scott on this, and there's a more recent paper with Oleg Gnedin on it. As far as I know, it's consistent with the observations, including the distribution of globular clusters, the properties of the stars in the nuclear star cluster, and everything else that I know of. Now, more background on nuclear star clusters. They typically inhabit flat galaxies. M87 doesn't have one. And that's interesting, because mergers, I believe, are extremely uncommon in the real universe. They're very common in topics on theoretical astrophysics, but they're very uncommon in the real universe for low mass galaxies. For very high mass galaxies, maybe a quarter of the mass comes in like that. But for galaxies like our own, it's probably a few % of the mass has been added in mergers. In stellar mass has been added in mergers. And it's clear that nuclear star clusters would not survive very well in a merger, because the black hole that is in another galaxy would come in, and as it came in toward the center, it would tend to disrupt the nuclear star cluster. The relaxation for time for dynamical evolution, you can compute from the number of stars, and the collision time for physical interactions are comparable to the Hubble time in the central regions, central parsec of galaxies. So just you expect from the numbers of what you see that both these processes might be important. And finally, they contain massive black holes, and the black hole mass scales roughly proportional to the nuclear star cluster. I mean in a very crude sense that an Andromeda has a higher mass black hole than our galaxy, etc. So this implies to me that this is a good environment in order to make the black holes. And so what Nick and I did is explore that possibility. And what are the problems normally in making massive black holes? Well, the first one, which we all know of, is if you just, this Sultan argument, which I think is extremely powerful, tells you that most of the mass in observed massive black holes, not these massive, came from accretion of gas. I think that's without question included. But there are very few that are accreting at more than the Eddington rate. So that the Eddington time is a half a gig a year, and the duty cycle is in fact a few percent, i.e. most black holes are very, very quiet. So they're not accreting at the Eddington rate, so it's very, very hard to grow them. But they're found at high redshift. So this is the classic problem of how do you make them in the time available. Another problem is that the black hole properties are tightly correlated with the galaxy's spheroid properties, though the scales differ by 10 to the 5, and you wonder, how does one know about the other one? And then an interesting fact is, if you go below a certain mass, and the evidence for this is still not certain, you find many galaxies without black holes. And the lower bound is on the order of 10 to the 5 solar masses. So if you had a mechanism to make them, the seeds, it might bring them up to 10 to the 5, and the Sultan argument doesn't apply to very low mass black holes. It's an integral argument and applies to only high mass black holes. So what you might look for is a mechanism that makes them around 10 to the 5 solar masses. So now, what are the physical processes? With these two sets of clues, what are the physical processes in nuclear star clusters which could make black holes? So we see a lot of O stars. They're going to leave 10 solar mass black holes, and you can easily compute there have to be a very large number of them in the centers of the galaxies. Many of them will get kicked out, it's true. But if you make any kind of a computation, there'll be a significant number there. So these are seed stellar mass black holes from normal stellar evolution, given the observed O stars and the frequency of galaxies which have O stars like this. So we know the duty cycle of having early type stars in it is not tiny. What are the dominant dynamical processes that would occur in such a nuclear star cluster with these seed black holes? Well, one is interaction with binaries. And we all know that. What will happen is the black hole will wander by a binary, get into a three-body interaction, eject the lowest mass star at the velocity, orbital velocity, say 200 kilometers per second, and then the binary with the black hole and the remaining star moves off in the other direction at 20 kilometers per second. And if that's more than the escape velocity, it will leave altogether. If it's less than the escape velocity, it will just oscillate and come back. So one is interaction with binaries. The other thing with a large cross-section is tidal capture. And this may not be very familiar with everyone in the room. But the physics of it is extremely simple and very well defined. Imagine here's a sitting 10 solar mass black hole. Another star comes by in an unbound orbit, but comes by close enough to raise the tide on the star. If the energy that goes into that tide is equal to the energy that it had at infinity, then it's bound. And then it comes back in tighter and tighter orbits and will end up in a circular orbit with twice the original closest distance. So now that's the tidal capture process. Many people have worked on it. The details of it remain, as far as I know, fairly uncertain. So, for example, there's an awful lot more energy dissipated during the in-spiral than the original capture. How much of that can be radiated away, and how much of it ends up with more mass loss? Not really very well known. So, it might be that because the energy that's deposited in this, it is not deposited in the center, it's deposited in the outer layers, from which radiation is relatively easy. So the work that's been done gives a limit of about 40 kilometers per second, where that will eject the black holes. But if the escape velocity from the system is more than 40 kilometers per second, then the binaries will not eject the black holes. So then we're looking at tidal capture as the criterion. So let's follow that up. So we have analytic and preliminary numerical sims show that a runaway will happen. Since the tidal capture cross-section goes as a power of mass steeper than 1, if it starts to run away, if a black hole captures many stars and eats them, and its mass grows, doubles, well, then the cross-section from more tidal captures is higher and higher, and the process will run away. So it's super exponential. What limits it? Well, it eats up all the stars in the core, and then the density of stars that it can interact with is lower and lower, and so it eats further out, and it gets to a limiting rate. This can happen only if super Eddington accretion of tidally captured stars is possible. So do we know that that will happen? No. Do we know that it won't happen? No. My expert on this is Jim Stone. Is he in the room? Who's made very similar calculations with students, and he says he thinks it's likely that they will, for the same reason that black holes form within stars. When the density of gas is high enough so that radiative trapping occurs, then the Eddington limit is not at all important, and you just accumulate everything. But it slows when the nuclear star cluster core is eaten and the limiting black hole seed mass is reached. And you can predict what masses you get, and it's in good accord. So here's some data, which was taken by Georgiev and Boker and other papers. One is on the mass of the black holes that we see, the density, the relaxation times, and what you notice is relaxation times are about 1 billion years here. That's the most important one of these figures, with some of them at the high end, in observed nuclear star clusters. So, and you can compute whether in observed nuclear star clusters you'd get tidal runaways, and what you conclude is that in the observed nuclear star clusters, if there weren't black holes, you would very often get tidal runaways. And we go through so it's not a fantastic, you're not assuming initial conditions for this process that don't occur in nature. You can look at the observed nuclear star clusters, and they're appropriate. And a simple formula that you get out of it is this. Notice density doesn't appear in it. Only the velocity dispersion appears. That it saturates, and the mass goes as t to the half times the velocity dispersion to the 3/2 power. Then it's a simple formula. We derive it in the paper. Look hard at it, what's in it and what's not in it. Basically, the only thing that's in it is the velocity dispersion of the cluster and time, and the mass of the stars that you're eating, which we're assuming is about half a solar mass. So this is what you get. And it comes out to be 10 to the 6 solar masses for a 50 kilometer per second velocity dispersion and 10 to the 10th years, which is just about right. So the simplest back of the envelope calculation gives you that you run away to masses that are similar to this is very close to the mass seen in our galaxy and Andromeda. Now this is a very interesting figure from what? Well, you can look at this next figure and see. Okay. So this is the data from Jenny Green and many other papers on velocity dispersion and the mass of the black holes and the mass of the nuclear star cluster. And the stars are the nuclear star cluster, and the dots are the black hole. And so our galaxy is here. Wait, our galaxy is here. Here's the black hole. Here's the nuclear star cluster. Here's Andromeda, the black hole of the nuclear star cluster. And these are all the other points. And the line is the figure I just drew, is the formula I had on the previous chart. So the line is this. And what you can see is it fits fairly well, except at the high end, where the black holes are much more luminous than that, orders of magnitude, and that we know is the case. They grew by accretion of gas. So then below a certain point, here's 40 kilometers per second, we see black holes, they're only upper bounds, and there are nuclear star clusters. So the evidence seems to say, this is just empirical evidence, that below a certain velocity dispersion, you either have very low mass black holes or don't have these seed black holes. There's only upper bounds. Then there's a range, which is normal galaxies like ourselves in Andromeda, where the formula fits and you have just nearly what you'd have for the Runaway. And then there are high mass black holes where the nuclear star clusters are much lower, in fact lower in mass if they exist at all, and you have very high mass black holes. And those we know grew by accretion via the Sultan and also Scott Tremaine's argument. So below 35 kilometers per second, the upper limits. At around 35 to 150, they follow the line for saturated growth. And then above that, they are growing by other means. So I'll just conclude, and then I've left lots of time so that there'll be questions. I think nuclear star clusters are likely for the sites of the black holes, both in the cases when they do have them and when they don't have them, it works. For those below 40 kilometers per second, the black holes are ejected due to interactions with binaries, and there's no runaway. For those above 40 kilometers per second, the stellar mass black holes can grow to 10 to the 5 to 10 to the 6 promptly via tidal capture. And it looks like they can do it in enough time, in a short enough time. Now there's two open questions. How rapidly do the nuclear star clusters form? We don't know that empirically because we don't know when globular clusters form, and we don't know how globular clusters form. So even if they come from inspiraling, we don't know when they form. And the second thing is we don't know for sure whether they can accrete the gas at a super Eddington rate. The best guesses are that they can from tidal capture. These are the seeds for the massive black holes. So this is the summary, and I'm open to questions or comments or criticism.